Hi, I'm Xavier Deroy. I'm a postdoc researcher from the Delft University of Technology in the Netherlands. So in this video, we talk about our research on commonality-driven test case generation. So this is joint work with Bjorn Evers, Boria Directionfar, and Designman. So search-based unit test generation has been around for quite some time now. Tools like EvoSuite are able to generate a test suite for one or multiple classes on the test, and the generated tests are effective for coverage and fault finding, can also find real faults, and are useful for debugging. So EvoSuite takes as input a class on the test and the jar file of the application to test, and it starts by generating a random initial population of tests that is refined using a genetic algorithm, and eventually produce a test suite when all the test objectives are satisfied or when the time budget is exhausted. So despite the many advances, there are still several challenges for search-based unit test generation. Among those challenges, so the crafting of complex objects and values that are used in the test, for instance, as parameter for different method calls, but also the coverage of encapsulated elements in the code. So various approaches have been used to overcome those challenges. So for instance, constraint solver to generate complex objects and value allowing to execute some specific part of the code, but also techniques like seeding, where information from either the source code or the existing test suite are used and provided to the search process in order to overcome the different limitations. So in this research or hypothesis is that common and uncommon execution paths observed during the actual operation of the system can lead to better guidance of the search process and hence better coverage. So to test that hypothesis, we define two secondary objectives called common and uncommon that can be used for search-based test generation. So what do we mean by commonality, and how do we provide that information to the search process? Well, in general, search-based unit test generation, like tools like EvoSuite, represent a portion of code using a control flow graph. So nodes and edges denoting the different possible control flow in the code. So what we do in our approach is label the different nodes in the graph with execution weights. So the execution weights denotes how common is the execution of a specific node in the graph. So based on this execution weight for a test case, we define a commonality as a sum of the execution weight balanced by the number of nodes and the highest and lowest weights in the graph. So if we take the following example, let's consider a test that traverses the following nodes and edges. If we apply the formula, well, the execution weights are given for the different nodes, but we also need the highest execution weight in the graph, which is 10 in this case, and the lowest execution weight in this graph, which is 1 in this case. So applying following the formula, we have a commonality score for this specific test of 5 out of 6. So, great. We can define commonality using execution weight for the different nodes in the graph. But how do we get those execution weight? Where can we get them from? Well, one way to do it is to look at the logs of the application of the test and trace back the different log messages to the portion of code where the log instruction appears. And based on that, just simply count the number of times we see the different messages and label the different nodes in the graph. So based on the execution weight and the commonality score, we define two secondary objectives. So the classical secondary objective for unit test generation is test case length. So if you have two test cases that have the same fitness, you will look at the length and you will keep the shortest one to avoid an explosion of the number of method calls and instruction that you have in your test case. So of course this property is still valuable for us. So what we do is basically balance test case length with commonality in the following formula, where you have two meta parameters, alpha and beta, allowing to define the importance that we want to give to test case lengths compared to commonality. So we evaluated our two secondary objectives, and for that we defined the following research question. So first we look at how does the commonality score of the generated test compare when using common, uncommon, and default secondary objective. Then we look at the structural coverage, and more specifically how does the line and branch coverage of the generated test compare when using common, uncommon, default secondary objectives. And finally we look at the fault finding capabilities of the test by looking at how does the mutation score of the generated test compare when using common, uncommon, and default secondary objectives. So for evaluation, we consider one system under test called JabRef. So JabRef is a graphical Java application for managing BibTeX and BibLaTeX databases. It's open source, the source code is available, and so we used it in our evaluation. So how did we do? Well, first we instrumented JabRef in order to add logging instruction in the source code. Then we gave it to 5 users and we asked them to use it for various tasks. We collected the logs that were produced by the instrumented version of JabRef. We also sample 150 classes under test, so the 150 classes as classes under test. So for that we took 75 classes with the highest complexity in the JabRef project. We took 38 additional classes with the largest number of lines of code, and 37 additional classes with the highest number of executions based on the log that we collected. So we implemented our two new secondary objectives in EvoSuite, and we so gave the logs and the class under test as input. And for each one of the classes, we use the default common and uncommon secondary objective with the MOSA algorithm for a time budget of 3 minutes, and we repeated each execution for each class under test 30 times for statistical significance. So we collected the test and the coverage report produced by EvoSuite in order to answer our different research questions. So to analyze our results, well, we first filter out the classes for which we had less than 30 successful execution run with EvoSuite, which leaves us with a total of 104 classes. For each one of those classes, we evaluate the fault finding capabilities of the generated test using PIT. So for that we executed PIT with default configuration on those different test suite and collect the mutation analysis report. So we compute the p-value for the different test suites using the Wilcoxon rank sum test with alpha of 0.05 and the effect size using the Vargalani statistics. So looking at the commonality score, we see that indeed the common and uncommon secondary objective have an impact And well, when using common as a secondary objective, the commonality score is higher, and uncommon, well, the uncommonality score is higher as well. So looking at the structural coverage of the different test suite, well, the common and uncommon secondary objective have very few impact on the structural coverage. However, it can still improve the branch and line coverage in some specific cases. Same observation for the mutation score. So on average, commonality and commonality has a very low impact on the mutation score. However, it can again well improve the mutation score in some specific cases. So to summarize, how does the commonality score of the generated test compare when using common and common default secondary objective? Well, common and uncommon secondary objective impacts the commonality. Looking at the structural coverage, well, commonality and commonality secondary objective have a very low impact on average, but still has some large impact on very specific cases. And future research will focus on systematically identifying those specific cases to know when is it interesting to use commonality and uncommonality. Same observation for fault finding capabilities. So the mutation score, well, there's a very low impact on average, but again, in some specific cases, you have a very large impact that is observed. So that's it for our results. So what are well the future work for commonality-driven test case generation? So in our first about the execution weight. So in our evaluation, well, we got the execution weight from an instrumented version of ChabRef, which provide us exhaustive data about the common and uncommon execution path, but it's of course quite expensive to execute and collect. So one possibility would be to collect those data from operation logs. So if you, for instance, are in a DevOps environment, those operation logs should be readily available. Well, the downside, of course, is that depending on the logging practices for the application of the developer for the application under test, well, those execution logs might be incomplete. So for the commonality score itself, for now, it's based on the individual execution weights in the control flow graph. So it's easy to implement and to compute, but it might not be representative of actual behavior. So one way to overcome this would be to base the commonality score on partial execution paths. So basically looking at sequences of nodes that are covered by the test, and based on those sequences see if that sequence is common or uncommon. So this of course might be more representative of the actual behavior of the system under test, but it's also harder to collect and compute. So last but not least, the end goal of a test suite is of course to identify faults when the code is updated, but also to help a developer to debug his code. So one thing that we did not assess in our evaluation is the influence of common and uncommon behavior on the understandability and the fault localization capability of the generated test. So this is left for future work. To conclude, so in this presentation, I presented our research on commonality-driven test case generation. Our hypothesis was that common and uncommon execution paths can lead to better guidance. So for that, we define the notion of commonality for a test based on the execution weight in the control flow graph. We implemented our approach in EvoSuite and evaluated it on JabRef. We saw that if indeed common and uncommon secondary objectives have indeed an impact on the commonality score, it is much more limited when it comes to structural coverage and fault finding capabilities of the generated tests. And finally, our future work includes more investigation on how to collect execution weight, how to refine the notion of commonality for a test case, and finally assess how commonality-driven test case generation impacts understandability and fault-finding capabilities of the generated tests. Thank you for watching this video. I hope you enjoyed it. So if you want more information about commonality-driven test case generation, don't hesitate to read our paper. The replication package is also openly available on Zenodo, so do not hesitate to take a look. And if you have more questions, well, you can also send us an email. We'll be very happy to answer. Thanks.